Okay, so this is going to be the support video for 3.4, where we're dealing with questions 5, 6, 8, 11, 13. I'm going to look at question number 8 and 13 with you to kind of get some basic groundwork for these. It says a person in good physical condition can put out 100 watts of useful power for several hours at a stretch, perhaps by pedaling a mechanism that drives an electric generator. Neglecting any problems of generator efficiency and practical considerations such as resting time. Okay, so let's just assume we got this figured out. So that every time I had to take a break, someone swapped me out, and it was, continuous. How many people would it take to run a 4 kilowatt electric clothes dryer? So this is just for your household dryer. How many people is it going to take? Well, we know that 100 watts, okay, is what I'm able to produce. Okay, that's the rate at which I'm able to produce electricity, and I need to come up with 4,000 watts, and one person comes up with 100 watts. So you just think about this. Okay, if that's what I need, and I've got 100 per person, if I just divide by 100 watts, okay, it would take 40 people pedaling a little bike in order to produce enough electricity to power my clothes dryer. Now that's for however long that works. Now my clothes dryer might take 45 minutes to an hour, and so for 45 minutes to an hour, I need 40 people pedaling a bike to produce enough electricity to turn my dryer on. That's not a great option. We are not great producers of power. We fatigue, and just our ability to produce that power is not amazing. Well, let's go a step further. Let's say that we want to replace a large electric power plant that produces 800 megawatts. Well, 800 mega means times 10 to the 6th, so I'd add 6 zeros divided by my 100. Okay, you can kind of per person, right? Cancel those out. Then you look through, and you end up with, I'm off by one. Let's see, 800 megawatts divided by 100 takes 2 zeros off. Did I not get enough zeros on there? No, I did. Okay, there we go. Boom. Right, there's the other comma. 8 million people. And when you consider that one of these large generators, large power plants, does not supply electricity to 8 million people, you got to realize electricity has to be produced in large quantities, and we don't, as human beings, have the ability to do that. So if you've ever seen the video, a movie or a joke video or something like that, where someone's pedaling a bike to produce electricity, it doesn't work well. We're not efficient enough. We can't produce enough energy quickly enough to be able to power anything beyond maybe a light bulb here or there. It's just not enough. And so that's a big issue. When we talk about energy consumption, we have to find other ways to produce the energy. And then question number 13, how long will it take an 850 kilogram car with useful power output of 40 horsepower to reach a speed of 15 meters per second, neglecting friction? And then what if it also has to climb a hill? So just up front, we want to understand, power equals work over time. And if we think about the work as a change in energy, okay, in part A, we're going from not moving to a kinetic energy state of 15 meters per second. So we can say that our power would equal a change in kinetic energy over time. And we're looking for that time. Well, the power, we're told, is 40 horsepower. Now 1 horsepower is 746 watts, so it's just 40 times 746. So I'm going to do that real quick. 40 horsepower times 746. Okay, that's how many watts I'm going to have in the vehicle, equals 1/2 the mass of the vehicle, which was 850. This is a pretty small car, times the velocity squared, and that would be 15 squared, all divided by t. I'm going to rewrite this after we do a quick calculation. 40 times 746 gives me 29,840. 29840 equals, and then I'm going to take 0.5 times 850 times 15 squared to produce a 95625. 95625 over t. Again, this is one of those cool opportunities to use the old Welch rule. If you don't know what I mean, you're missing out. But we just switched the t for the 29,840, and the time it takes would be 95625 over 29840. Let's do a quick calculation. Be this number divided by that number. Made it with 3.20 seconds. Now, that's when we're just driving along the flat road. If, however, our car rises some distance upward, and I think that's what we end up with in the second part, it says that we're going to end up going up a 3 meter high hill. So if we're going to go up 3 meters, then the idea of power being work over time, again, work being a change in energy, not only is the engine producing a change in kinetic energy, but it's also producing a change in potential energy if we go up a hill. And so when we talk about this energy transfer, we still have the power being 29840. That's the 40 horsepower times our 746 conversion rate. But now instead of doing kinetic energy, we're also going to have our potential energy. So 1/2 850 times 15 squared plus mgh 850 times 9.8, and we've raised our mass by 3 meters, all over t. The calculation is the same process, but because we're adding the amount of energy production that's required, because we've got to go up the hill as well, we're going to slow this process down. It's going to take a little bit more time. So that being said, I hope that that's enough to get you through and get you ready for class. All right, thanks. See you then.